SwayamPrabha. Digital India. Educated India.
Okay, welcome back. So in the last lecture we described the AA standard assumption, which would be useful for our analysis for the gas power cycle. So here let me first review the reciprocating engines. So this is a illustration of reciprocating engine which is shown here. Okay, so the inlet valve is this, where of course your gas, the fuel will be injected, okay, and the exhaust valve would be where the combustion gas would be removed. Okay, so this is your top dead center, the position where the piston forms the smallest volume in the cylinder, and the bottom dead center is the position of the piston where it forms the largest volume in the cylinder. So that means this piston keeps moving from the BDC to TDC, and the length of this TDC and BDC would be, or the difference between TDC and BDC is basically nothing but the one stroke. So this is the stroke is nothing but the largest distance of the piston which can travel in one direction. Okay, the diameter is called bore. So as I already mentioned, the inlet valve and exhaust valve. Now if you take this piston to the TDC, there is certain volume which is also left. Okay, and this volume which is left is called nothing but the clearance volume. Okay, and this the volume which you can displace from BDC to TDC is nothing but your displacement volume. We will be making use of compression ratio in our analysis, which is nothing but the ratio of the maximum volume to the minimum volume. Okay, and maximum volume of course corresponds to the BDC. So volume corresponding to BDC is the volume formed in the cylinder. Okay, that will be the maximum volume, and the volume corresponding to TDC of the cylinder, that means the empty volume, would be the minimum volume, because this is the top dead center. Okay, so this is the ratio will be considered as compression ratio. We will be also making use of something called mean effective pressure, which is nothing but a fictitious pressure that if acted on the piston during the entire power stroke would produce the same amount of net work as that produced during the actual cycle. You can see the illustration here. So if this is the complete cycle, okay, this is the complete cycle here, the corresponding work is W net. Now this net can be written as some fictitious pressure, which is this multiplied by the difference in the volume. So essentially this itself would be your effective W net. So that is what we are referring to, effective pressure in the system. So which is nothing but if you look into the formulation, MAP multiplied by displacement volume, and hence MAP is nothing but W net divided by the difference in the volume, Vmax minus Vmin. Okay, so as I already mentioned, you have internal combustion and external combustion. So this is going to be internal combustion based analysis, where you can consider two forms of reciprocating engines. One is a spark ignition engine, where the combustion of air fuel mixture is initiated by a spark. This is basically engines in most cars, the gasoline engine. And the other one is a compression based ignition engine, where the air fuel mixture is self ignited as a result of compressing the mixture above its self ignition temperature. This would be the case for diesel engine. Okay, so we will be first considering the spark ignition engines. Okay, so this would be your 4-stroke internal combustion engine, particularly spark ignition engine. So let me first go through the basic the actual process, and then we will try to represent this actual process by a simplified cycle, which we will call Otto cycle. Okay, so in this one particularly, internal combustion engine consists of 4 strokes. So this is an example of 4-stroke internal combustion engine, and essentially this complete cycle consists of 4 times of this one single stroke. So you can clearly see 4. So the direction shows that this is 1 stroke, 2 stroke, 3 and 4, as well as the crankshaft completes 2 revolutions for each thermodynamics cycle, because you can clearly see here it will be your 1 revolution and this will be another revolution. Okay, so let me start from initially what happens. So let me start with this particular first image. So here you have this inlet valve. Okay, so this is your inlet valve, and this is your exhaust valve, right? So here if we can consider that this is the point you start your cycle, okay, initial point of your cycle where the inlet valves open, and hence you allow your air-fuel mixtures to come in, expansion. So this is your inlet valve which opens, and this gas intake is considered here, and upon here the compression stroke takes you to the point where it's sufficiently compressed that you can start your ignition. So this is where the second state, okay. So ignition happens, this ignition initiates the combustion ends here, okay, and after the combustion this expansion happens. So the combustion ends here and this expansion is shown by this stroke, so this becomes the second part of the stroke. Then the exhaust valve is open. Once your exhaust valve is open, this would be your exhaust stroke, so essentially the volume gets reduced, and then your air-fuel mixture is again replaced here, okay. So you pass the air-fuel mixture which will expand the volume, which will be intake stroke, okay. So this is your intake valve open, so this becomes your intake stroke, which is actually this. So though we are starting with the compression stroke, okay, we can also start from this analysis as an intake stroke. So let me again go through this explanation again. So here the first step corresponding to this image is nothing but your compression stroke, which is this, okay. So this is your compression stroke, okay, followed by your expansion stroke, followed by your exhaust stroke, followed by your intake stroke. Now this becomes a complete cycle. So you have compression stroke, expansion stroke, exhaust stroke, and intake stroke, okay. It is very clear that this is not a closed system or not a closed thermodynamic cycle. This is open because your air-fuel mixture is renewed again. But what we are going to do for this analysis of such a 4-stroke internal combustion engine, that we will consider it to be a closed thermodynamic cycle, and this can be considered by an ideal Otto cycle, where this compression stroke can be considered as isentropic compression. This whole combustion will be considered as a constant volume, considered to be very fast reaction, and hence the energy, whatever the combustion occurs, can be considered as a energy from the external medium, that is you're going to be Q in, okay. And the first part with the compression itself, which happens in the combustion stroke, is considered to be adiabatic, so that will be your isentropic compression, okay. So this is your adiabatic reversible compression, and this is isentropic, followed by heat addition. Here this combustion is considered as a heat addition, so we are making use of a standard assumption, and then followed by your isentropic expansion, and then followed by your heat rejection, okay. So in other words, what we have done is, though these particular images are not exactly in the same stroke, okay, but so what we have done is that overall cycle which involves this trap as in actual 4-stroke spark ignition engine can be represented in idealized cycle based on a standard assumption, and this will be your ideal Otto cycle, okay. So this becomes your Otto cycle analysis, and this is your PV diagram for that. So let me go through a simply more subtle points of this Otto cycle. So Otto cycle, we will be considering the 4-stroke engine, and this cycle can be assumed as an ideal Otto cycle. Here we are going to make use of a standard assumption. So essentially ideal Otto cycle consists of 4 internally reversible processes, as we already described earlier. So this is the first would be your isentropic compression, followed by constant volume heat addition. So the combustion is going to be considered as constant volume heat addition, then isentropic expansion, followed by constant volume heat rejection. The exhaust gas which is taken out of the system will be considered as constant volume heat rejection. So here the corresponding PV diagram again. So this we have already looked at. The corresponding TS diagram would be this, okay. So 1, 2, 2, isentropic compression. This will be your constant volume heat addition, isentropic expansion, constant volume heat rejection, okay. Now we can make use of thermodynamic analysis by considering that kinetic energy, potential energy changes will be 0, and thus your energy balance for any process based on the unit mass can be simply considered here, that this will be your Q in minus Q out, net Q in minus net Q out is equal to simply your change in internal energy of the system. It's considered to be a closed system. So as we know that no work is involved during the heat transfer process, since both are operating at a constant volume. Okay, so this is at constant volume. So we know that Q in, for the case of a constant volume, considering this is air, is simply delta U, and similarly Q out is also delta U, and thus since delta U can be written in terms of heat capacity and change in temperature, we can write this expression Q in terms of CV terms, CV and change in temperature. Now for the case of thermal efficiency, we can write simply eta in terms of W net divided by Q in, and this can be further written by in this form. Now this is an ideal reversible cycle. We can replace the Q out and Q in terms of CV, and this is what you get. And this can be written as in the ratio of T1 and T2, and then these terms will come as a separate one. And one can show that considering this 1 and 2 and 3 and 4 are isentropic process and this constant volume, and based on this ideal gas relation of the ratio of temperature to V2 by V1 to the power K, where K is nothing but your Cp by Cv, one can show that this term goes to 1. Eta auto, okay, for thermal efficiency is nothing but 1 minus T1 by T2. Okay, compression ratio is nothing but V1 by V2. Thus this can be also written as 1 minus 1 by R K minus 1. Okay, that is what is written here. Now based on this expression, it's very clear that if one can increase the efficiency by decreasing R or increasing K. So you can have more R in order to have higher efficiency. This is a typical range for the gasoline engine, somewhere from 7 to 10. And as I said, you can increase the efficiency by increasing the heat capacity, which essentially means that you can use working fluid with a higher specific heat ratio in order to have higher efficiency of Otto cycle. Okay, so you can make use of this analysis of ideal Otto cycle based on air standard assumption, and based on this particular cycle definition and its analysis, one can do certain examples, and this is an example which we can try. Okay, and the idea of this particular example is to attempt by describing the process on a PV diagram and making use of different energy analysis which we have done and represented. So enjoy by doing this example, and I'll see you in the next lecture where we are going to describe the diesel engine concepts. Okay, so I'll see you in the next lecture.